Hi, I'm Sophie Kowalik, and this is my lab for circuits. So to outline what I'll go over, I'll have my purpose of the experiment, some things to know, my data, my calculations, and putting it on a graph, and then answering the what if and why questions. So the purpose of this experiment is to predict the behavior of circuits containing resistors, and then use meters to measure the actual values of the current and in the circuits. A preview of what I found out was that the node rule and the loop rule are true from our calculations, and the RC was independent from time. So things to know, the loop rule is delta V equals 0 round trip. The node rule is that the current in equals the current out, and Ohm's law I'll use for calculating, which is V equals I times R. So the first part of the current simulation was to change the conservation and energy conservation. And to do that, I predicted what the circuit 1 current would be, and I said that I1 would equal I2 because of the node rule, which ended up being correct, and it was 0.02. And reversing the direction of the ammeter caused a negative value. And in circuit 2, when I disconnected one of the ammeters, it became 0 because the circuit was open, and we found that the voltage was 3. And these were with 1.5 volt batteries. So my data for this, I found delta V between each point. Each connection was like, this was A, this was B, B to C, C to D, and so on. And when I plotted the delta V's, what I knew it should be was 0 because of the node rule. Oh, no, because of the loop rule. And so I did get 0 when I combined all these together. So why doesn't the ammeter change when attaching the voltmeter? It's the voltmeter is so large that the current running through it is so small that doesn't really affect it. This continued. The overall current increased when adding another one in parallel with the 100 resistor. The second task was the RC circuit, and this was, I had to collect data for my graph. So when the battery is connected to the tin bulb and the capacitor, the light bulb lit up and it slowly began to dim. However, removing the battery powered the light bulb when I added a voltmeter. And then I found the time and charge it took for the capacitor to charge, and for the 10 it was 9.9, for the 20 it was 20.1, and then I did it for it to discharge, and I got 10.2 and 21.2. Once I graphed my data, I plotted the natural log of delta V over delta V0 in order to find the slope of -1 over RC, which we were looking for RC. RC is the time constant of the circuit at which the voltage difference has dropped to 1 over E from the original value. And this was the reason I did 30 times 0.2 is because I did 30 was the omega of the light bulb, and 0.2 was the I. And as you can see, I got pretty consistent values from my experiment and the predicted. So the what if questions. So what if you were doing this lab in real life and use an actual ammeter instead of an ideal one? So the current reading would be lower on the ammeter because they have an actual resistance. However, and the online one didn't, it just said it was 0. And if you were doing a real battery with no resistor in the circuit, the capacitors would take much more time to charge than the instant one online when you connect it with the battery. In conclusion, my results showed the node rule and loop rule worked when I got delta V equals 0. And if there's any error, it's because when I used the timer, maybe my times were off, so that affected the slope of my graph. And the online simulator, as we stated before, has a 0 omega. and a real life one would be different. Thank you.